Okay, so that whole last lecture was, the whole point was to just expose you to the differential machinery that happens when people try to describe fluid motion. And that's great. It's really meant for anyone that maybe will go on to graduate research to see, right, how these expressions come about. So I looked over at my notes when I took the course, and it was actually pretty brushed over as well. So I was feeling a little bad that maybe I didn't do as well describing these things. But besides just a couple calculations, this whole class never really focused on that stuff. But it has to be there because I can't not let people be exposed to that if they want to go on to do more of this, more rigorous fluid analysis stuff. But this kind of where it begins of this applied part. And that's kind of getting at, like, what should we try to describe in terms of pipe flow, in terms of external flows, right? So I think it's nice to start with just the look of it, right? What are we trying to describe right now? And there are just some key things that people realize by just doing experiments and seeing that things are fundamentally different based on certain numbers. Okay, so right, some just key things are, right, you can look at laminar versus turbulent flow, right? And there's experiments and there's numbers that can quantify these things, right? You also can look at how flows entering a pipe and consider things that are called entrance effects. And that will be more rigorous later, and it involves those differential terms we talked about before. Other things is when people zoomed in on surfaces, they found these really boundary layers, right? Dottery layers, right? And you can kind of look and observe these. And I posted some videos actually that kind of maybe show some of these things happening, which I like watching, because you can kind of see how fluid can just behave. And these are just sort of things that we need to describe. Other great experiments are sort of separations of the boundary layers. So if you put a sphere in a body, you'll see that there's this like turbulent wake where something happened, where past the sphere something changed drastically. Much later, really, we'll try to describe, right, a shock wave, right? You can see that on jets that accelerate really fast. You can just see these extremely sharp lines that represent these shock waves that occur because the thing is moving so extremely fast. So I'll try to put links on just looking at these things in video, because I can just draw something on this board, but I always like to watch fluid motions to kind of see, like, well, what's your goal? Your job as some sort of analyst is maybe to at least quantify that phenomena that we do see. But in this class, right, one thing that we should all definitely know how to calculate is something called the Reynolds number, right? And this Reynolds number comes about from pipe flow experiments, but we'll just, right, I'm sure you've all seen it before, right? That's the equation for it. Another way this is written is you just nu like that, and this number is just this. There's dynamic and kinematic viscosity. And some people like to work with this number just because it makes equations look simpler, actually, and I think there's measurements reasons for that too. We all have our own descriptions, I would say, of what this non-dimensional number means. So it's non-dimensional 1, and you can do that verifying the units themselves. You just need to remember what the unit of that one is as well. And but you can interpret these things, or this equation of what it's describing, in a couple ways. So there's classic one is right. It's a ratio of these inertial forces, and the inertial forces is really that MA term on the other side of equations. That's the inertial force. That's what's happening. It's force equals force. So inertial is the MA term. So it's a ratio of that over these viscous forces, and the viscous forces were a term that popped up where it was right in the Navier-Stokes equations. It's this term right here. So this is a viscous force. So Reynolds number can describe, right, how much inertial force, how much viscous force are apparent in some sort of system. But you can do other ones too. Actually, you can look at it as can look at it as a ratio of time scales too, actually, which people that research turbulence actually like to think of it that way as well, where a viscous time scale and a convective time scale. And the convective time scale is that in the material derivative, this part is the convective part that people will talk about. Even that, very crudely, you could just kind of think of this as turbulence over what I have, turbulence over, maybe just say that to yourself, or it's a measure of something like that. So right, you can rationalize Reynolds numbers in many different ways, but the fact is it's a non-dimensional number and helps you quantify things such as these entrance effects or laminar versus turbulent, for instance. We all know that Reynolds number, if it's really, really big, we go, oh, the flow energy turbulent. If it's really, really small, we go, ooh, we're in that laminar regime. But let's get to some